Anyway, so all right. So did you see where we came up with 602.11 amps?
I'm at the spot where we divided the 8304 over the 200,000 V has got 4152, and that's where I stopped at. Oh, you got a different answer then. How did you get the 240? What I do wrong there? 830.4 divided into 200,000 equals 4152.
No, something wrong with your calculator. Clear it real quick.
All right.
And then 200,000 divided by 830.4 should be 240.84.
24084.
Say that again.
24084.
Yeah, 240.84. Yep. Yeah, I don't know. Might have something stuck in your calculator or something. I don't know.
Okay, so then the 24.08. What did you do the next calculation?
Well, it's not 24.08. It's 240.
Oh, I'm sorry. 84. 240.84.
Yeah. And that number, that's the ampacity of that secondary.
Okay.
So
then,
the table value then kicks in or comes into play here, and that's what that 2.5 is from the table there on page 361.
We give the 602.1.
Yep. Now that number, because the 250 that we took off the table does not have a C note 1 on it, that means that we've got to round down. We can't round up. And the next standard size, technically the answer here is going to be that 601 amps because there is a 601 amp fuse size, not a 600 amp breaker necessarily. So in this case, the answer would be 601 amps listed there. That was a standard question that was around for a long time. And it was around even recently, so I know that it's still out there, but I can't guarantee that you'll have that exact question now because it's one of those things that might or might not. But it's good to know how to use these two tables for transformers. Just remember that under 2,000 or under 1,000 volts is the table that's on page 362, and there if you're doing you just follow the table depending on what they give you in the conditions of the question. You'll be able to find the right multiplier pretty easy. Okay. These next two are important ones, and they're going to take a little bit of work. What did you get on those next two? The general lighting and demand load for the bank there, and for the office space.
8.6 is what I got in my final answer.
Really?
Took the 1600 and the general lighting load. With the receptacle is 3.5, so I times that, which gave me 5,600. Then I times that by the 125%.
Excellent.
Which gave me 7,000. And then the receptacle load, which is the per square footage, which is by 1.
Yep.
Gave me,
there you go.
7,000, and then the answer 8.6.
Yeah, you nailed that. There's a lot of things that could go wrong on that question, and you nailed every one of them correctly. So that's awesome. Were you pretty familiar with that stuff, or was that did you just kind of look that up on your own as you went through last night?
What confused me before when I started on this one is that normally the general lighting load is 3 without the receptacles, but with the receptacles included, they held at 0.5. Correct?
For banks or what? No, the only thing on that table that has anything other than lighting is just dwelling units, and then there's I think like extended stay suites have both receptacle and lights in there. But other than that, they're normally it's just lighting.
Yeah, but I thought the general line item without receptacles included is just 3 VA.
For residential dwellings, yeah.
Okay.
Yeah, the table that you got that from was you know the tables and everything where you got all that from, right? Or were you doing that from memory? 220.12 on page 68, I think, maybe 69. Page 68, yeah.
Yeah.
And so this is lighting only is what this table is. The exception being that they do include receptacle counts in the dwelling units because of that little letter A that's next to the word dwelling units. But for banks and office buildings, that 3.5 VA is for lights and for nothing else.
Right.
The fact that you got that as continuous duty is impressive because that's something a lot of guys miss. All right, and then the receptacle note that you got was off of K, 220.14K right there on page 69 under K2 there, left-hand column, page 69, 220.14K2, the 1 VA per square foot for receptacles. And that's because we know that banks or office buildings are going to have an inordinately large amount of just general purpose stuff plugged into the general purpose receptacles. So because of that fact, you have a minimum threshold number that's at least 1 square foot times 1 VA, no matter what, for the power loads for any kind of a bank or office building. Whereas, for example, for a retail restaurant or retail store or something like that, you wouldn't have to worry about receptacle load calculations at all if they didn't give them to you. You wouldn't even have to even they wouldn't even be on your radar. But in this case, we have that as code minimum. So the next question then should have been pretty much a piece of cake for you. Then a bank with a space of 15,000 square feet includes 102 receptacles. What's the minimum computed demand load for general power receptacles with this occupancy type?
Okay, so I went to page 70 and reviewed the information there.
Okay.
What I have is the 102, which is receptacles, at 180 VA. Gave me the calculation, which is 102 times 180.
Yeah.
But 360. And then at the 100% plus 50% off the remainder, gave me if I subtract 10,000 kVA of the first 10,000.
Yep.
And then, which gave me from 18,360 gave me 8,360. Then adding in or multiplying the 50%, which gave me the 4,180, which gave me 14. Adding the other 10,000 back in gave me 14,180.
And then the rule that you had just a minute ago, on the question above that, we had that 1 VA per square foot, right? For an office building.
Say that again?
The question above that, the one that we just did just a second ago for the office space.
Yes, sir.
You added 1,600 volt amps, right, for the receptacle loads in that question, right?
The 50% is what I added.
No, not the one that we're doing right now, but the one we just got, the 1,600 square foot one that we just did. Yeah.
Yes, I added the 1,600. No, wait a minute.
Yeah, the last step that you did was you added 1,600 volt amps, 1 VA per square foot, right?
Yes, and plus the 7,000.
For the lights and stuff. All right, so my question for you is this. The banks with the 15,000 square foot, if you're looking at K2, does that change your answer from 14,180 to 15,000?
Say it from the two you said?
Well, if you're looking on page 69, right, of your code book.
Oh, okay.
The note K basically tells you you got two calculations to do. The first calculation that they tell you under K1 is to take the calculated load from 220.14I, which is what you just did, right? You took the 180 volt amps per receptacle times 102. You got that 18,360 number. And then you were correct in going to the next page in that table that has a derating factor on dot 44, and you did derate it, and all that was correct. But what you were doing, what you're performing in doing that and getting a number that was 14,180 is exactly what K1 tells you to do. But it's got to be calculated to be the larger of 1 or 2, which means you've actually got 2 calculations to do in that question, because you've got a bank that's either going to be your calculated value, which is the 14,180, or what's K2 tell you?
K2 is 11 volt amperes or 1 volt amperes. So larger of 1 or 2. Right?
Yeah, the larger of the 2 calculations. So the first calculation that you came up with, the 14,180 volt amps, is exactly what you should have done for K1, but K2 trumps that in this case because you got 15,000 square feet in the question.
Okay.
So 15,000 square feet under K2 would have been 1 VA times each square foot. That gives you a value of 15,000 volt amps.
Okay, so I'm not understanding that one. So
okay. All right. So what I'm doing here? Let's just look at it this way. Let's say that this was not a bank. Let's just say it was a restaurant, right?
Okay.
So if this was a restaurant, and if I had 102 receptacles times 180 volt amps, my total connected load would have been 18,360 volt amps. And then you derated that by taking the first block of 10,000 of that away. The balance was 8,360. You divided that by 2, or took 50% of that number and got 4,180. Then you added the 2 numbers together, the 4,180 plus the 10,000. You came up with 14,180, right?
Correct.
Kind of like that, or however you did your own writing.
Yes, sir.
You did the same thing in this case on that bank, the exact same thing with the bank, which is what the instructions to note K2 or K1 tell you to do, is this exact same math. But with banks or office buildings, there's actually 2 calculations that you have to do. It's this calculation that you just did, but you also have K2, which is whatever the square feet is of that bank, times 1 VA per square foot, which comes out to be 15,000 square feet, times 1 VA, which comes out to be a number that's 15,000 VA. So what you're looking at is 2 different calculations, 2 different numbers, both of them that fall under 220.14K. The instructions there in K are you have to take the larger of those 2 numbers.
Okay, so you got the 15,000 square feet times 1 VA per square foot, right?
Right.
They use the 15,000, and then that 15,000 goes into what now?
Well, you did 2 calculations. You did the 14,180, and then you did the 15,000 under the second calculation.
Okay, so then my 15,000, I'm going to go ahead and take away the 10,000.
No, you can't derate it. You can't derate it.
Okay, then I'm confused then. So the second calculation is 15,000 times the 1 VA.
Look at it this way. In a bank or an office building, you have to have at least a square foot expressed in volt amps. You can't have a number any less than that, no matter what. So that's a non-deratable number. It's a threshold that the code says you got to have at least that many volt amps. So the fact that this bank has 15,000 square feet, 15,000 times 1 VA, that 15,000 volt amps is a minimum code requirement that I have to have no matter what.
Okay.
Now, if the number of receptacles is also given to me, well, I have to calculate that out as well. So there's 2 calculations going on here. Whichever one ends up with the bigger number is the one I end up having to keep. So you can look at it as, note K, I can derate, the first note there, or K1 I can derate, but I can't derate K2 because that's the minimum threshold value, of, in this case being 15,000 volt amps. So I'm really, your math that you did is correct, and I don't want you to change that, because you should do that every time, because that is the first of the 2 calculations that you have to do for banks and office buildings, is that derating, under the table on dot 44, and your 14,180 VA would have been correct had this not been a bank or an office building that had 15,000 square feet. That last fact there, that 15,000 square feet, that's a number that you can't derate. So you're stuck with that 15,000 volt amps is the bigger of the 2 calculated values.
So then after doing the 15,000 square foot to the 1 VA...
Then you can't touch, that's done.
But that's the total answer right there. There's nothing else from that answer?
That's right. That you got to have at least that. Or if your calculated value, like I said, if there had been 170 receptacles, then that number would have been bigger after you did your derating than your 15,000 square feet at 1 VA would have been, and you would have had to choose that as your number. So you can derate the stuff that's under K1.
Okay, so then
let's say this bank had 162 receptacles, right?
Right.
If I had 162 receptacles here instead of 102, is it not going to let me change that? Huh. Oh, no, because it's just a copy of my PDF. Well, if I had 162 receptacles instead of 102, then the math would have been 162 times 180 VA.
29,160.
What'd you have? 29 what?
29,160.
And then I would have taken the first 10,000 of that away like you did, would have left me with 19,160, and I would have divided that number in half, which would have given me, what would that be, 8,000...
9,580?
9,580. And then I would have added the 10,000 back to that number, so I would end up with 19,580 volt amps doing that calculation. So I would have derated those just like you just did, take the 10,000 out. But then when I go back and look at K2, the square footage times 1 VA, I'm still going to have 15,000 volt amps for that calculation. So I've got 19,580 on one calculation under step 1. I've got 15,000 under step 2. In that case, the bigger number there would have been my 19,580, and I would have chosen that as a minimum calculated value.
Okay. So now if it wouldn't say bank,
that's right,
then it's the calculated one that we did the first time.
Would have been right on the money. Yep.
So
yep.
That's another thing I need to pay attention to.
Yes, sir. And they will give you, and I'm telling you, sometimes they'll give you, I've seen a question that's the exact same question where it's an office building that's got the same 102 receptacles, but they don't give you the square footage. It's just they give you an office that's got an unknown determined amount of square footage, and it's got 102 receptacles. Exact same question. Even the answer blocks are the same answer blocks. It's the 18,360, the 14,180, the whole amp. And in that case, because you don't have a square footage to know what that second calculation is, then you can't derate it because you don't know where to stop. Because in other words, you can derate the receptacle load as long as you don't derate it below the square footage value.
So then without the square footage though, say we're looking at 102 receptacles but no square footage. So we're going to take that value of 102 times the 180.
Yeah.
And that gives us our total value of the 18,360.
And then stop right there because you don't have any idea where to stop the derate. You don't know, there's no way to do anything else for fear of dipping below the square footage, so you just leave it at 18,360.
Okay.
You will see a question that's similar to this in some form or fashion. So you're going to see some receptacle calculations where they throw stuff like this just exactly like that. So knowing the difference between an office and a bank and anything else is important because this is the only one that this applies to. Otherwise, your steps that you did are perfect and right on the money. So just keep that bank and office building in mind. There's one more calculation while we're on this subject of receptacles that I need to make you aware of, and let me see if I can give that to you real quick. I'm just going to draw it out, probably be the fastest way to show it to you. This is one that was kind of hit and miss for a while, but now it seems like it's been on everybody's test. So they give you a single piece of hospital equipment or a crash cart. I'm not sure what the equipment is that they're giving you, but they're telling you that you've got all these receptacles on the same piece of unit equipment. And they're giving you 3 singles. I'm going to draw it out. So let me just draw it out first, and then I'll show it to you, and it'll make better sense than if I just tell you about it. This is an exact question. These are the exact numbers. So this is something that, once we're done with this, you can just jot down the answer. And if you run across this question, then you'll know what the answer is, and you just answer it and keep rolling. I mean, so I'm no problem with that. They basically give you this setup right here, where you've got on the same piece of equipment 3 singles, 4 duplexes, and 2 quads, and they even tell you that these quads are 4 receptacles in each quad, so they're trying to confuse you, but it's basically like this right here. Okay? So in your code book under 220.14i, which is on page 69, that's right above that bank or office building stuff, that 180 VA per yoke that you were using earlier, that's where you got that from. 220.14 right?
Right.
All right, so right after that, the second sentence in that section tells you that a single piece of equipment that has multiple receptacles, 4 or more, on the same piece of equipment changes from 180 VA per strap to 90 VA per actual receptacle opening individually. So in other words, these are still going to be the same because 90 and 90 on a duplex are still going to be 180. So whether I'm doing that by the strap or the gang or by the receptacle, this is still 180 VA, but these up here would only be 90 VA per receptacle. So instead, huh?
Even the quads?
The quads would be 180 VA each gang there, so you're looking at 360 VA for each one of those quads because you're doing 90 VA per receptacle. But
Okay.
you know, like I said, the regular calculation is still going to be, you know, basically the gang of the box is what you're doing that 180 VA against. So you'd you know, down here on these you'd be doing 180 times 2 anyway, whether you're doing them, you know, all together on one piece of equipment or if they were on a wall. Either way, the only thing that changes are these little unis up here at the top. So you end up with 90, 90, 90, and then 180, 180, 180, 180, and then 360, 360. So that the numbers are just like that, and you just add those up. And if you don't hit 10,000, there's no derating to take on it. So just be whatever that value comes out to be. That'd be the number.
Okay.
But they will have one of the answer blocks will have these three up here at 180 VA because that's what we normally do. But the only reason why this changes because they're saying it's all on the same piece of equipment, so it's on a crash cart or something like that, not on a wall.
Okay.
And so that's what. And so let me just do the numbers on this real fast, just so you'll know what the answer is, and then you just write it down. Let's see. So we're looking at 90 times 3, which is 270. I should have known that without having to do that. 180 times 4 is 720. And then 360 twice would be 36 be 72, right? 720 also? Yeah, it'd be 720 also. So you're looking at 720 plus 720 plus 270. So 1710 is the number there altogether. And if they're giving 2 kVA, it'd be 1.71 kVA. All right, 1.71 kVA. Write that down because you may run across that exact question, and that way you can just answer it and be done with that one. And this bank with 15,000 square feet with 102 receptacles is an exact question as well. So it's one that you might just those are the exact answers that they have on the question if you have that question. So I mean you'll see that exact thing. I'm not 100% sure about that 27,863 or whatever that last answer is, but I mean it's just something that they made up out of their air or something because I don't even know how they managed to get that big of a number. But all right, that's that. All right, I think we've got that covered, and you've got a pretty good handle on that. The resistors and the Ohm's law stuff. Do you have you did pretty poorly on those on your first test. Have you had some time to kind of go back and study that afterwards, or? All right. There's a simple formula for resistors in parallel where you just have 2 of them, and so the resistor total. When I just have 2 resistors in parallel like this one is, or like this pair is, that resistor formula looks just like this. It's the product over the sum formula.
Okay, so it's what's that top line? I can't.
It's R1. Is that better? Sorry.
R1
times R2.
2 divided by R1 plus R2. Okay.
So in this case, what you've got is they're telling you that they're kind of painting a picture of it, but this boils down to an Ohm's law question is what it is. I've got a 12 ohm resistor. I've got a parallel 20 ohm resistor. In parallel on their surface, what's my resistance to earth? So basically, what's my RT value? So RT is going to equal 12 times 20, 12 ohms times 20 ohms divided by 12 ohms plus 20 ohms.
12 divided by.
Maybe it's 12 times 20 divided by 12 plus 20.
Okay, what?
It's 12 ohms times 20 ohms divided by 12 ohms plus 20 ohms.
12 ohms times 20 ohms. And then, what's the bottom line?
12 ohms plus 20 ohms. I wrote that a little bit better. Maybe that helps some.
Okay, and then what's the RT value?
That's total resistance. So when I'm done here, I'm going to do the top line. So I'm going to do 12 times 20, which is going to give me 240, I think, right?
Yeah, 240.
And I'm going to divide that by 12 plus 20, which is 32. So 240 divided by 240 divided by 32.
7.5.
And that's my answer. 240 divided by 32. That is the total resistance value in ohms. .5 ohms.
Okay, so 12 resistor parallel. Okay.
So the keys to that test question to kind of get your traction on it. First and foremost, they're resistors and they're in parallel. Okay, so parallel resistors, and you're looking for a total resistance value to earth, so total RT with two parallel resistors. That anytime you see a question like that where they don't give you the volts value or don't give you any kind of other number to work with, and they're just talking about resistors in parallel, and there's just a pair of them, that's the formula to use. So it's a formula you'll have to write in the back of your book because they don't give it to you. So it's kind of a handy one to have around in case you need it. And that's all there is to it. It's a pretty simple Ohm's law question when it comes down to it. It's one of the more simple ones to deal with once you know the correct formula to use with it. So just make sure you've got that just kind of in the back pocket there. All right. 40-foot tall high bay manufacturing building. What's the maximum length of unprotected conductor that shall be permitted to run without standard protection devices were installed indoors dedicated to a particular load? Should be to the following. So we're talking about, an unprotected conductor. What the definition of a tap conductor is a conductor that's protected in a manner that it would not be, protected in that way in other normal circumstances. So if you look on page 94, the definition of a tap conductor.
Okay.
Under 240.2, as used in this article, a tap conductor is defined as a conductor other than a service conductor that's had an overcurrent protection ahead of its point of supply that exceeds the value permitted for similar conductors protected as described elsewhere in 240.4. So what they're talking about here in that question is a tap conductor. And so 240.21 B, 240.21b on page 98 of your code book. Tap conductors are listed there. Number 4, B4 on page 98, it's the bottom right-hand column, the bottom of the page there, is taps over 25 feet long in a high bay manufactured building that's over 35 feet tall or 35 feet high at the walls. And under number 2 there, you're allowed to have a tap conductor 25 feet long horizontally and not over 100 feet in total length.
Now, one question is on the. I know we had the taps highlighted in our index in the front of the book, but for something like this, is that something I should make note of to know where to go look on that?
Yeah, there's a little section in 240 dot. Look on page 90. 95. On the bottom of page 95 under 240.4e, there's a little article that lists a bunch of tap sections in the code book. So it's kind of a nice running list of just different sections that have tap calculations. Motors are not listed there, so you'll want to write in a note to yourself either on the bottom of page 95 or at the top of 96. Single motor taps they've got listed on the number 6 there, but it's actually going to be 430.28 is really where your tap conductors for motors are going to fall under. So just put motor taps, see 430.28, page 331 if you'd like.
We got that highlighted.
Yeah, it's highlighted there. And so you'll see that for 240.21 is listed there. And then there's a couple of other notes there. So, I mean, that's a good place as any, I guess, to kind of put notes for taps. But just you'll have to remember where that's at, I guess. But
Okay.
all right, so that's a pretty simple, straightforward code question. So the next one is what's the minimum size branch circuit conductor necessary to feed a 20 horsepower design class B 3-phase 480 volt motor with a 75 degrees Celsius maximum rated terminals. Again, I'm telling you, Lance, when I get a motor question, the first thing I do is ignore everything in that question except what is it that I'm trying to size. And I'm telling you, you got to force yourself to do that every time because you got to filter those questions somehow or another. And so, what are we sizing here?
Branch circuit.
Yep, just branch circuit for one motor by itself, all together. In the notes that you have in the page 5 there, where single motors, branch circuit wires are going to be on page 329. On page 329, on the left-hand side, you had a note that a continuous duty motor would be a table FLC times 125%. And at the bottom of the page, you had some notes about the small conductors being a little bit worth a little bit more amperage than they normally are. You've got a note that tells you tables are on page 350 and 351. So your process here would end up being to go to page 351 for this 3-phase motor. 20 horsepower under the 480 volt or 460 volt column, which is where that 480 volt motor would fall under, would be 27 amps. I take that 27 amps, multiply it times 1 1/4.
Wait, okay. Here's where I messed up because I thought if the continuous run, I went ahead of 175 is where I went.
You went what?
I did a 1.75 because it was a continuous run. Does that make a difference?
No, the 1.25 is for the continuous duty. Again, that 175 is a breaker number, so it's got nothing to do with wire.
Okay.
Yeah, you got it stuck in your head from that other question, and so don't feel bad. But it's 125%, and again, that's from page 329. You got a note, should have a note at the top of your page there under 430.22 is where we got that number out of on page 329.
Yeah, single motor conductor, single. Yeah, the Y-star delta run motor, 100% motor full load current as determined by 430. Okay, and then the load.
Now that's a Y-star. You're talking under C there specifically, but at the very top there under 430.22, just a little further up the top of the page there, where it says single motor.
I've got it on the page. I didn't highlight the.
Okay.
25%. I just did the pages that were to the side of it. All right, 125.
And that's what I've got. Even on mine, in the front of this book, I've got single motors conductors, page 329. That way, I've got all my notes here. All right, so it'd be 27 amps, wasn't it? Is that what it was on that? motor?
33.75.
32.75, and that ends up being a number 10, because remember, number 10 is good for 35 amps for a motor conductor. So I'm going to use number 10 there, where I would normally use a number 8 for anything else, but because it's a motor, and motors are excluded from the small conductor rule, I'm going to use a number 10 conductor that's got an ampacity of 35 amps.
Oh wait, okay. So 33, 35. We went to the higher value, 35, and that was on 161.
Page 161. Now, on the bottom of page 329, you should have some notes to yourself about those three conductors being, 14,
yeah,
12.
Says 14,
20 amps.
20, and then 14 odd, 20 amp, 12, 25 amp, 10, 35.
Yep.
So, yeah, we're 35 is 10. You're right.
Yep.
Okay.
And so, bada boom, bada bing. That's that one. This is kind of the way I've got my code book written. I guess we went over that yesterday with yours, so yours probably looks just like that. So, all right. This is how did you attack this question here? This 100 horsepower motor with 480 volt 3-phase motor. How did you deal with that one?
Let's see. Page 351 where I started at, and I went to 40 volt 3-phase, and it gave me the value of 124.
Did it bother you about the efficiency and the 1,000 watts per horsepower or anything like that?
No, again, because I was reading what I thought the question was asking was what the horsepower motor.
Your answer is correct, so don't let me talk you out of it. You did exactly what you should have done. You went back to page 352. You pulled a motor FLC value off that table, 100 horsepower, 460 volts there on the column. It's 124 amps, and that is the correct answer. It's just they're trying with that question. They're trying to get you to do some calculations, but if you look on 430.6, which is on page 324.
Pretty what?
On page 324, specifically under 430.6A1, it tells you that table values have to be used to determine ampacity of conductors.
For less than 20. The table values.
Where's this table values there?
And then what do you highlight on that one?
The third line there where it says at the end, it says table 430.28, 249, 250 shall be used to determine the ampacity of conductors or ampere ratings of switches, branch circuit, short circuit, ground fault protection, instead of the actual current rating marked on the motor nameplate. And that's the code rule that says we do not use motor nameplates to size wires, switches, disconnects, breakers, fuses, etc. We use table values. So they're trying to. That question is designed to get you to do the math, because if you do the math, 1,000 watts per horsepower times 100 horsepower is 100,000 watts. At 480 volts, if you divide it out, it comes out to be like 128 or something a little bit different than what the table value is. So you did right by ignoring all that and just going straight to the tables and dealing with that. All right. The next one is a manufacturing process, 3-phase, 480 volt, 100 horsepower squirrel cage motor protected by non-time delay fuse shall have what size maximum overcurrent protection device selected? So walk me through the process on that one.
Okay, so page 351, look at the 3-phase, 40 volt, 100 horsepower, was 124.
Mm-hmm.
But then again, I did wrong because I was at 175 when it should have been 125.
On what? Say that again?
I did the calculation at 175% instead of 125.
Well, okay, now remember, the 125% is for wire. 125% is for wire, and we're doing that because that conductor is, subjected to some heat load because it's under load for more than 3 hours at a time. Breakers, though, breakers aren't continuous duty consideration. That's the breakers are on page 335. So when you're looking at that test question, you ask yourself, what are you sizing here? And you're sizing overcurrent protection, the breaker or fuse, right? Breakers and fuses, the notes that you have in that on page 5 would be to go to page 335.
$335. Okay, so a screw cage. Okay, so we're at 175%. Oh, I'm sorry, 225. Oh, wait a minute. No, I had it right, 175. No?
You're close.
Okay, screw cage other than design B under dual element. Oh, non-time delay.
There you go.
Okay, 400. I'm sorry, 300.
300, that's right.
I'm looking, I had highlighted you told me to run the notes from exception number 2. I put in that space and I wrote the 400. So that's why. Okay. So
yeah.
300.
Yeah, it'd be 300%. So you're taking the 124 that you got back from page 351, multiplying that times 300%, and then you're going to round that down to the next lower size breaker.
So it gave me 3720. So you said rounding down is 30. No, wait.
So it'd be 124 times 3.
Oh, 350 amp.
And then that gives you, what's 350, you said? No, 375? 124 times 3. Yeah, 372. And then that rounds down to a 350. 350 is the next lower breaker size under 372.
Your audio went down.
Oh, you can't hear me? Hello?
I can hear you very little.
Okay. I'm not sure this is going to help or not.